All right, now it begins. Lifting problems. Now, once you get the setup, it's not too bad. I know as a student, actually, these ones didn't freak me out too much once you get the point. They're reasonably mellow once you get it, but man, there's a lot of stuff that's going to go into this. So let's just start it. We need to talk about some things called mass, density, and gravity. So let us begin with the fact that mass, we're going to use an M, but I'm pretty sure you know that. But this is our new little piece, is we're going to start talking about this rho. Put it off to the side. I kind of draw it weird. Rho. It has to do with density. And what is density? Well, it's the mass of an object per unit. So maybe you have a rope. And we know that it's 1.5 kilograms per meter. So that would be for essentially a one-dimensional sort of idea. And then later we're going to get into some stuff where we're talking about kilograms per volume. When we start pumping water or pumping beer out of something, or maybe you're sucking down a margarita, we'll be talking about the volume. But for right now, we're going to deal with some stuff with like a rope or a chain hanging, and we're going to lift it up. And how much work does it require to lift up this rope or chain? Now, we're also going to be discussing our gravity, and gravity is G, right? Gravity is our G. Acceleration. And then we're going to find that mass is actually equal to the density times the length. And I put quotes around it because it can also be used in a different way. We can say it's the density per volume, but not for this one, depending upon what units we're using for our density. So let me ask you a question before we jump into all this. So you're on Earth, you know? And then there's somewhere called the moon. You've heard of that, right? Do you believe in the moon? Do you believe in birds? Do you believe the Earth is round? I hope so. Okay, I'm getting off the topic. So let's say we have an object, and let's say I weigh 100 pounds on Earth. Actually, let's do it this way. Let's say I weigh 100 kilograms. Sorry, the conversion would be rough for me to try and do. So that would mean that you'd be about 220 pounds on Earth. Now, gravity is 1/6, roughly, of the Earth's gravity. And of course, gravity is negative, but all the work we're going to do is going to be the opposite direction, so we're going to keep it all positive. So then I ask you, I'm like, okay, cool. Well, how much, let's start with pounds. How much do you weigh on the moon? Well, you'd be 220 pounds divided by 6. 110 over 3. Cool. So how many kilograms would you weigh? And I'm using weigh. You should not use that term at all. How much do you weigh on the moon? You weigh 100 kilograms. Like, what? Why? Maybe you already know this. Pounds is already a force. Kilograms is a mass. They're two different things. Well, while we can convert them, like I can say, hey, because I'm on Earth, I already know what pounds are on Earth. And I know that 1 kilogram is approximately 2.2 pounds. But one's a mass and one's a force. Pounds require the force of gravity, and it will change it. But mass is the same thing no matter where you go. All right, there's my little spiel on that. And now we're going to get into lifting problems. Oops. Sorry, these are all the same things that I did in class. So you're getting the same lecture, same problem, same everything as if you were in an on-ground class. I did them last week. Now I'm showing them to you. So I got some practice, so maybe I can know what the heck I'm talking about. So let's start here that work is equal to the force times the distance, right? The mass times gravity times some distance y. And I'm using y because we're going up and down over here, right? Up and down, up and down. Y values. I mean, you could change them to x's, but then you'd have to change your whole idea. But as we learned, our mass is equal to the density times, what was that again? Let me look. Oh, times the length. Times the length. Okay. So we're changing our mass into, oh geez. Into rho times delta y. Why is that delta y? Well, let's jump over because we're thinking about some sort of chain that's hanging down. We got a chain that's hanging down. We want to lift it up. So in case you haven't ever seen this before, them being facetious, we're going to break this into little teeny tiny pieces. Just our certain lengths. Oops, I don't want that one. We're just going to break them up into pieces. Equal pieces that are delta y. Delta y. So we're only trying to find the work. I wrote little w sub k saying we're just looking at this little distance here. So our force times our distance here. Well, or I'm sorry, not that. The length. Well, that length is delta y times whatever the density of said rope, chain, whatever the heck's hanging down there. So we've taken care of these two. There's our gravity. And then the work, we got to know how far we're going to travel, the distance. This is our distance. Well, we're going to think of this L as the total height. Like maybe this is 11 meters high. And then maybe our y sub k, maybe that's, I don't know, 5 meters. So how far is it to go from 5 meters up to 11 meters? It's 11 minus 5, or L minus y sub k. And that's going to be our game over and over. And then, as always, we're like, well, there's not just one of these things. We need to add up all of them to get the total work. It's just like finding the area underneath curves when you did Riemann sums. Just like we set it up for length of curve. Just like we set it up for surface area. Just like we set it, everything we've done. So we're going to add them all up. We take our old delta y, we slap it at the end. We have these two constants hanging out. And then once you take the limit as n tends towards infinity, we break those up into infinitesimally small little things. We end up with our integral. And here it is. This will be our formula for lifting problems, where L is the total height. Y is the, I guess I'll say the current height. It's going to be our variable that we're going to be working on. Rho is our density. G is our gravity. And we look and we say, oh, yeah, we got to go from wherever we're starting on up to L. For this one, because, well, we started from something being at 0 and we went up to L. All right. Let's see it in action. Actually, I think since it's been 9 minutes, I'm going to stop here and we'll do this problem next. So we don't give you too long of videos. And this is what we're going to mess with. A 10-meter chain with density of 1.5 kilograms per meter hangs from a platform at a construction site that is 11 meters above the ground. Compute the work required to lift the chain to the platform. And this is our game. So we'll come back in the next video, and this is what we're going to start with. So hopefully this got you a little understanding, and it might be going over your head. It's okay. It's all right if it's going over your head. But what you need to be able to do is you need to be able to at least have the formula down and be able to use it. All right. See you in the next.